Today's topic is vector space, and I will deal with Euclidean vector space. Mathematicians and scientists they distinguish the vector and scalar. If I written of something, the vector has the starting point and the end point, and we usually represent a vector to an arrow, and we will so it has a length and it has a direction. So we will this arrow as a vector, and in this sense it might be trivial to show the length. It is easier than direction, because if we find the value of the length, then we can write. First, I will use this notation firstly. The start point to end point vector length is it is easy. However, the direction case, it is hard to express to some number, and so mathematicians wanted to develop how to understand all these vector, and so in this section we will deal with the vector and the space of vector, and it will be called the Euclidean vector space. And so in this section fairly close to geometry, in my opinion. And so first, I will introduce vector space, and I will extend. I will generalize from the vector space to two-dimensional vector space and three-dimensional vector space, to n-dimensional vector space. Because we are living in three-dimensional world, and so it is quite familiar, and the physicists they develop some information of vector in two-dimensional and three-dimensional. So we will generalize to n-dimensional the information of them. So I used this notation, and so let me explain more precisely. If we give I will preview a vector. We used about vector in the previous chapter, so I used the notation VB. Let V be a vector, and having 2 points. One is the tail point, tail S, and having the tip is endpoint, and we will say this is initial point, and this point is terminal point. However, I do not prefer to use this notation initial point and terminal point because we have equivalent or equal in vector. So if there are two vectors, it is one v1 and v2 starts from S prime and it will be end to E prime. So if S and S prime is not equal, then we might think these two vectors is different. However, if the length of two vectors and the direction of two vectors is same, that means if you move this vector to same initial point, then if they have same direction and same length, then we will say the two vectors are equivalent. So in this sense, we write this by writing starting point and end point having arrow. However, I usually will use just V, bold V or V. It means having equivalent if you move to the origin or to standard point. If you choose one point, and then you can translate the vector to this point, having this point as a starting point. So if you move this point, I will see that because after we define what is vector space is a very convenient notation. So in this case, it might not be equal. However, if you see equivalent, it is we will read them to equal. So we are working in algebra, and algebra is similar to addition. So algebra needed addition, subtraction, multiplication, so we will define them. Firstly, let us see the additional vectors. Firstly, if we see in 2-dimensional or 3-dimensional world, then it is quite makes sense. The vectors or 3-dimensional, space or dimension. Then if we write v plus w, then that means we have two vectors, and usually we will use parallel rule. And if you have two vectors, then you can draw the parallelogram by using two vectors, and the antipoint of start point will be the end point of v plus w vector. And this notation you can see the another way. If there is v vector plus w vector, and by translating the v vector to have the initial point as the terminal points as the initial point of v, and so finally it is same same notion to the previous definition, because we construct parallel graph, and in this graph it saves these points, and it means it does not depend on choosing what we will translate, because if we translate w, then it will give same value. So if we define like this, it will be well defined. And also, if you consider the zero vector, then zero vector will not move in there, and so that means w vector plus v vector plus w vector is same to w. And also I explained it does not depend on the choose what we will translate, so also it will give commutative or addition. And subtraction is also similar, because when we construct addition and subtraction in real number or complex number in number system, the subtraction is inverse element of the addition at the elements. So the vector subtraction is defined by minus vector of w, and so we already defined the vector of v, and that means it has same length with w, and it has converse direction from w. That means if we give w like this, then and if we set the length is L, then minus w is minus w has same length, and this direction is converse way. And so if you draw two vectors, then we say the summation is these two vectors, and by making parallelograph we can get this vector, and we can understand the different way also. Like if you translate the minus w vector to by translating to this point, then minus w vector will be this form, and from this the vectors, if you consider the second definition of addition, then v minus w vector will be this vector will equal to this vector. And also we constructed scalar multiplication. We will construct scalar multiplication. And I state the length is a kind of scalar because it has real number, and the scalar multiplication will affect to the length, only the length. So let be a vector, and if I didn't write the dimension, then its dimension is in two or three dimensions. And let K be a scalar. And we will work in real world, only real world. So the scalar is in the real number. And so we will define the scalar multiplication of V is to draw the vector. And we explained in 2-dimension or 3-dimension world, it will be written as an arrow, and this arrow is V, this vector is V. And if we multiply K to I will left action. And then it will has same direction to V vector, and KV has length K scalar multiplication to L. So if you have one the vector which have direction 1, and if you multiply 3, then the length of 3V vector is has length 3 vector with same direction to V. And so in this definition, we can guess if you choose 1, the scalar multiplication by 1, then it does not change the vector. And so by defining these algebraic some operations, addition and subtraction and scalar multiplication, and actually it is not algebraic operation. However, it is needed in vector space, so I explained them. So as a proposition, we can see the associative rule in addition and subtraction too. Of course, scalar multiplication too. Associative rule. And that means we have 3 vectors v, u, v, and w be vector, and let k, m be scalars. Then we have the three kinds of associative two kinds of associative rule. One is u plus v plus w is same u plus v plus w, because if you consider the previous definition, then although you add one vector more, then just by translating to the result point, we can get the vector, and it does not depend on the order to add it. So it has associative row, and secondly, k. Hello. K, M, U. K and M are scalars, and if we scalar multiplicate first M and secondly K, it is same Km as multiplication in real number, and scalar multiply to the vector U is the same, because we define just multiply to the length of the vector. And so if we calculate the scalar multiplication first, it does not change the value of it satisfies the following equation. And also we can see the next property. It is distribute row. When we learned some addition and multiplication in real world, we have seen this property. I will use proposition. And it is makes sense in vector space case also. And I will add it at the expression of space. It is a set having structure. And so in this structure we have some data of the between the elements. So we are checking the property of the structure in real world and in dimension 2 or dimension 3 case. And so we will generalize to n-dimensional vector space, n-dimensional the real space. So I will use same notation, and then the distributive row means the scalar multiplication can be distributed. So k scalar multiplication to v plus w vector is same kv plus kw. So it is make sense the distribute to scalar addition. like that. So after we construct all these property and definition, we will define the axiom of vector space. So we are doing in dimension 2 and 3 now, and so we will see as an arrow. And then we sometimes write these vectors by using graph in real plane. If it was in two-dimensional vector, then sometimes we write the coordinate of the axis. One is x-axis, another is y-axis, and sometimes we write the vector by using coefficients, by using the real number of the each axis to each axis. So in this sense, we might be able to express the vector as a sequence of real number. Represent a vector V in two-dimensional or three-dimensional space with the initial points as 0, and it can be we can express the vector as an ordered pair or triple, like V1, V2, or V1, V2, V3. And that means the first, if we define the first axis is x and the second axis is y, then V1 and V2 means it has the coordinate V1, V2. It is analogously, you can imagine what is that. And so let me construct to n-dimensional now, and so since we use this coordinate system, and it is quite makes sense to generalize to n-dimensional concept by using coordinate. And so if we write this coordinate, it is necessary the point of 0. It is a kind of standard point. So now I will use the 0v, and it is also a vector, and it is zero vector. It is zero vector in this space, and the coordinate if its coordinates are all 0, then the 0v is called as the 0. Oh, I think I will explain coordinate first. We will define one more thing. Some vector in this business, we write the two-dimensional real vector space like this, and we will use the notation R to the 2, R to the 3, and R to the n, and this is n-dimensional R space. And so it can be written this form, and it's a we will define the vector in R to the n as a sequence of real number, n real number. If we be a vector. So in this sense, the zero vector is also an n tuple. However, its all entry is 0, and then it is called the zero vector in R to the n. Sometimes we call the entries in the vector as a component. Or 0. And in this sense, we constructed the equality in two-dimensional and three-dimensional real space, and it was if you translate the vector to have same starting point, initial point. So, and since we construct the 0 points in the space, so if we translate to 0 space, we might write the vector as a coordinate. So if we use the coordinate, we can define the equivalent of vectors. So I will use V and W notation. Let V be a n sequence of real number, and W is also n sequence of real number. That means it will be they are vectors in R to the n. Then if for every I the component was same, then we will say the vector is same because it has same initial point, and it's the terminal point is also same. That means the terminal point is same, so we defined it the same equivalent vector in two-dimensional or three-dimensional vector. It has same starting point and end point. So it is satisfied. It is a definition which is satisfied in two or three dimensional also. So by using this coordinate, we will generalize the addition and subtraction and scalar multiplication again, and it might make sense as a summation for each vectors, because we said if we edit two vectors, then we defined it as a parallelogram. And in this sense, that means if there was a standard axis, then these will be moved to these vectors v, and then each vectors will be the sum of its coefficient, each sequence number. So I will use the same notation. Let me define the addition of two vectors is addition of addition of each vectors, and scalar multiplication is also it will affect to the length of the vector, and that means if you scalar multiply for each vector, then in this sense, if you have coordinate in your word, each coordinate number will be scaled by the scalar k l x and k l y. So this definition makes sense in 2 or 3 dimensional also. And also next we defined the minus vector, and it is also similar to the the above definition, and since it has converse direction, so if you use coordinate system, then its coordinate will have minus value. And of course, subtraction, we define subtraction as by using addition, so I will use same definition. In this chapter, we usually construct y vector space has the axioms. There are lots of axioms in vector space. If you search in Google like this by using internet, and that is quite makes sense by considering these definitions and properties. So let me see the properties again. In R to the n, so let u, v, and w be a vectors in R to the n, and let k and m be scalars. I will do similar things in 2-dimensional and 3-dimensional world vectors property, because we defined from the 2 space and 3 space in real world, and we generalize from them, and so it has same property like commutativity and associativity. By using this notation, you can check easily them. And also the zero vector, if you plus, if you edit the 0 vector, then it does not change the vector. And also, by the definition, the minus is same to u plus minus u and is 0. Scalar multiplication is also has distributivity. So we have seen this property, and it makes sense in R to the n. K plus m, scalar multiplication to u, and u. So from this reason, we defined the axiom of vector space. And we can check by using this definition. It makes sense. So after this class, if you say vector space, we defined just in Euclidean vector space. So in Euclidean vector space, we can use the coordinate system. However, the mathematicians like generalizing to more larger world. So if by using this, if the space satisfies this property, then we will say it is vector space. And also, I think today is very elementary class. We can define by using addition and scalar multiplication definition, linear combination. I'll use simply if W is vector and we want to be n is also vector, and K1 to Kn is scalars or scalars, and we might sometimes written the vector W as the summation and scalar by editing and by scalar multiplying it for each other. Then we might construct the vector as the sum of them, and this form is called the linear combination. And that means if you have some vectors, and by constructing the summation as the summation of the vectors K2 V2 K3 V3, by adding these three vectors, you can get the vector W. And it is, I think, it is a kind of decomposition of the vector W, and in linear system, it is quite important decomposition. And I'm using the notation the sequence, and in the previous class I said this sequence can be written as a comma delimited form. That means V1, V2 just Vn, or and it is called row form, row vector, and we might be able to write horizontally, vertically, then it is called the column vector. And so we constructed the space of vectors in real world, real number, n r to the n. And so firstly, we say the vector has the length and direction, so we will focus the length and direction. And if you write the vector as a component, as a sequence of real number, then it might be not trivial its length. So if we by defining the notion of norm, we can get the length of the vector. And by defining the multiplication between vectors, then it is called the inner product. And by defining them, we can get the information of the direction. And so we will start in two-dimensional or three-dimensional vector space again. And we use the vector's length when we construct, when we get the number of the vectors. We use Pythagoras rule. It is what is it? I don't know the English. It is this notation. Orthogonality, maybe, right? Orthogonality, yeah. If it is orthogonal triangle, I think it is. It has orthogonal angle. Then maybe I have ever heard the word, but I forgot it. 90, yeah, having 90-degree angle, then its length we can prove its perpendicular. Okay. I will use 90-degree angle. If the triangle has 90-degree angle, then the Pythagoras rule said it's the length of diagonal line is square root of v1 square plus v2 square. Yeah, in more hyperdimensional, in three-dimensional, it is quite makes sense if you get the length of the vector by dividing three components, v1, v2, v3. We construct v1. We can calculate this length, and it is v1 square plus v2 square of square root of them. And by calculating this triangle, this length, since this length is 3, we can get the value of this length, the diagonal length. And so I will use this notation is norm by using line, for line. And so it means this vector is v and v's length is, this means the length of v. And in three-dimensional case also we will use same notation. It is length of v, and it will be for each square in square root. And so we might be able to define in R to the n space by using this notation, because it just plus one component, and so we define the norm of vector v as the square root of for each vector's squares, summation of for each vector squares. So be a vector in R to the n, then the norm of v is denoted. I use the notation, this notation, and is defined by square root of v1 square, v2 square, by adding v2 vn square. So from the rule of Pythagoras, we can imagine it will give the length of the vector v. In this sense, it is same absolute value. However, if you consider another space, having another space having another distance, like we are using, sometimes we use the norm of 2 and norm sub 2, and this means this form. However, we might consider another norm of v after we develop more advanced linear algebra. Then if I construct 3, then it is cube summation of each components, and by doing 1 over 3, this to the 1 over 3, and I think it is not good notation. I will use 4 because it might have positivity. So we in this sense, it will be drawn the different measure. In metric space, vector space is in metric space, and by giving different metrics, we can measure differently. So that means when in the two-dimensional space in over R, then usually we I will start the origin. If we measure the length of these points. Then by using circle, oh, it is circle. By using circle, we might calculate the length. However, if we consider the another distance by using elliptic circle, elliptic, like this form, then if we construct this one has length 1, and by scaling multiplication to L and L prime, if we scalar multiply L, then this point might have L length in the elliptic measure system. So by choosing different norm, we can, since the vector does not change it, since the vector has not changed it might have different lengths. And so first I said we will calculate the length. However, it is in Euclidean space. It is the sense of in Euclidean, and if you thought some weird word, in another, right, right. It is general term of abstract. Abstract value means usually we use just the space, Euclidean space, and so sometimes we use the complex number space. However, it is also kind of Euclidean space, so we use same notion of absolute value. However, norm is more generalized concept of absolute value. I bring example, or I recommend to watch my lecture notes because it is not difficult, it is not hard to understand yourselves. And we defined the norm of vector V, and so let me see the property of the norm. We sometimes should consider what is important information in this definition. So many mathematicians thought in this sense the absolute value is also has positive value if it was not 0, and so the generalized value norm is has also positive value if V is not 0 vector. And also in absolute value or norm, I said it will give the length of the vector, and that means if we give the 0 vector, then we want to be 0. Of course, we define the 0 vector. It has 0 entries in for each vector. So that means if the vector V was 0, then its norm is 0, and conversely, by considering the definition of norm, if its value was 0, then for every component, they should be 0 to have the value of 0. So it has if and only if property. And scalar multiplication case also, I said it will affect to length, and so we want to, it will be just by scalar multiplying, and give you a scalar. When we see the definition by scalar multiplying k, we will get for each vector is k, and we have distributive rule, and so it will give k the norm of v, and so that means v scalar multiplicated norm has absolute value of k multiplying the norm of v. So let's consider this property more, and I will explain one more. These three things, sometimes many mathematicians thought these three things are very important in norm system. So the mathematicians generalized if the norm satisfies these three property, then we will say that is norm, and their property is called the axiom of norm, or definition of norm. And let us focus on the third property. By using this, I explained when we calculate in elliptic points, I defined one length in the space, and by using scalar multiplication 1.L, we find the length of the point, and so by using this, I will define unit vector. It is length 1 vector. Unit vector is length 1 vector, and so called the unit vector, and so for every non-zero vector v in R to the n, if you define the vector u by using norm of v, then it is these are unit vectors. And this process is called normalizing, and sometimes we might say this normal vector. I think let us check the example. It is very important information in vector system. by constructing that unit vectors, we might remind the standard basis, because we define the standard basis E1 is 1 0 0 and E2 is 0 1 0. We defined this set. The collection of these is at the standard basis in R to the n. We used this notation in the chapter 1. And so the unit vector gives some convenient notation to express the vector v. So let me give an example and let me calculate them. So the vector will be written the sequence of real number. It is 2 2 minus 1, and then we can calculate the norm of v. By the definition, it is 2 square plus 2 square plus minus 1 square in square root, and it is 4 4 1, so 9, and its norm is 3. And by using this norm, we can make the unit vector by dividing this norm to the vector v. And that means 1 over 3, 2 minus 1, and it is scalar multiplication. The scalar multiplication will effect for each vectors, and so it gives us this vector. And by checking the norm of this vector, we will define this is u. Then the norm of u is 2 over 3 square, 2 over 3 square, plus minus 1 over 3 square. Then it is 9 over 4, 9 over 4, 1 over 9, so it will give the norm 1. So it is a unit vector. And so if we thought the norm of these each vectors ei, it has only one vectors and another components are all 0. So if you calculate ei's norm, then it will be 1, and so they are unit vectors, and these unit vectors set is called the standard basis. And if you ask why we are needed standard basis, is that if the vector was the sequence of real number, then by using the addition and scalar multiplication of vector in vector space, then it can be written by using the vector standard basis for every vector v in R to the n. So if you calculate something, then by using this basis, you can just consider the coefficient, and that means firstly I said it is hard to express the direction in the vector to real number because we do not know the way, as it is not information in real number or complex number. Sometimes we use the notation pi. We might construct the angle. However, it is also quite hard because if it is in two-dimensional real space, then it is makes sense by using pi. However, if it is in more hyperdimensional Euclidean vector space or non-Euclidean vector space, it is hard to find the direct. It is hard to define the direction. However, by using the standard basis or after this course, I will define basis. By defining them, we can calculate the vector by using the just coefficient. Then it does not mean by calculating this only coefficient, by calculating scalar, we can get the information of vectors. And I explained the distance when you ask the norm, what is difference between norm and absolute value. And so if I will show that if you have norm, then it will give distance which is called the length or distance. I think distance is very good expression, good term to express them. So I will give two vectors in R to the n. By using this norm, we will define the distance. Then we denote the distance between u and v by duv, and is defined we define the distance as having the norm of u minus v. So it is quite also makes sense when I explained the subtraction of vectors. When I explain subtraction of vector, there is two vectors, and the vector v minus w will be this vector, and we constructed the original point, and then this point might be said v because it has coefficients in real system, and this point also has coefficients. And this norm then will be given the value of the subtractions norm, like v1 minus w1 square, v2 minus w2 square in square. So this length gives the length of here, and so it makes sense by defining the distance by using norm, and it will give the length of the vector between u and v. And finally, we will explain the direction. We constructed how to calculate from coordinate system the length, and we defining by defining the norm of the vector, norm of vectors, we can get the length. And I will define the angle in the system. If we give two vectors, then it might have the angle of the vector of the two vectors, and so I will define how to get this angle from the coordinate system. And so we let us focus on in two-dimensional or three-dimensional real space, because we will generalize it, and we know that if the norm, I will say product. If you have two vectors v and w, and when we calculate in physics subjects, it's in a product. We say that is in a product, and it is defined by projection to w. Then w. I will use this notation. Then w and v cosine theta, and this is same to v sub w's norm. And by calculating this, we define the multiple of it is we define a function expecting two vectors and giving one scalar. So I will generalize from this because it gives the information of the angle, and so we see this information. This in a will be called in a product operator. So in R2D2 or R2D3 space, let U and V be non-zero vectors. And let theta be the angle between U and V. Then the dot product, or I said it is in a product, and we are work in Euclidean space, so it is called Euclidean inner product. Also, of U and V. I will use this. And it's defined. The dot product is defined as this form. Namely, in physics, they defined the dot product as the product by project to another vectors. And actually, if you project W to V, it will give same value because the scalar multiplication has commutativity rule, and that means it is same V W cosine vector, and it means WV. It's not normal. The normal WV by using this notation, we can get they are same, so it is well defined. And we to generalize them to n to the r to the n, I will focus on the property of the inner product. We constructed this term like that, and by using them, by calculating the norm of these terms, it in dimension 2 or dimension 3 space, it will be calculate. Now we use square. I forgot the notes to write in my notes on this. Squares. It is quite simple. By using this triangle, we have projected to another vectors. So by using Pythagoras rule, you can get the norm of you can get the distance of two vectors, and it is I use W. I will renote it is U. Then use norm square minus U projected use norm squares. It is U cosine theta, and so calculating the norm of U square subtract the norm of U cosine square, then it will give this length, and by calculating V minus U cosine theta's this length, by calculating square of this length, then it will give I will use different color. W, and this is I will use just length cosine 0. This is norm of W, and this length is norm of V subtracts norm of W cosine 0. And so U. And so U square minus U cosine 0 will be give this length. And by calculating, by adding the adding these lengths, it will give the length of the distance of between U and V. So we can think the property, this property, and it is sometimes quite useful to calculate cos the theta, and I will use that after. Firstly, we do not know how to calculate the inner product in coordinate system. So let me focus on calculating in two-dimensional vector space and three-dimensional real vector space. So let U is U1, U2, and V be V1, V2. Then we know the inner product in real system, and we defined it cosine 0. And by using this, by using in real world system, it is the value of 1 over 2 U square. I think I misnoted in my lecture notes. Plus V square minus U V minus U. Oh, wait. No. V minus U. Norm of V minus U square. And it is given from this equation by solve this equation, we will get U square and plus V square, and plus U square cosine square will be removed, and minus 2 U of the normal U cosine theta, and it was a distance. We defined it. The normal vector is this, and V. For this term, we can calculate the number of the normal U, the normal V cosine theta by removing that. I will remove this to this, and this term moving left side, we can calculate the number of this as the value of that. And we know the norm of this value, and it is the length of u plus length of v, and it is written the notation of each vectors in coordinate system, and is u1 u1 square plus u2 square. It's the square root and squares, and so plus v1 square v2 square minus v1 minus vu square plus v2 minus u2 square. And by calculating this, you can get the number of u1 v1 plus u2 v2. Similarly, in three-dimensional case also, by adding one more coefficient, one more real number, v1, v2, v3, you can calculate u in a product v is same this, and it will give the number of u1 v1 u2 v2 u3 v3, and so it gives the term of next coordinate, and inductively we will define the inner product in coordinate system as the sum of ui vi. And actually it will give the angle as we saw in 2 or 3 dimensional. So let u is u1, u2, un, and v u1, u2, v1, v2, vn in R to the n. Then the dot product, or I said inner product, of u and v is defined by u dot v is u1, v1, u2, v2, un, vn. And if you see this notation, then it is remark. You can see them. If you choose same vectors, then it will give the norm of the vector. v1 square, v2 square, so by calculating vn square, it is square of the norm of v. And if the vector was non-zero, then the norm of vector is also positive. And so we construct we defined the norm in coordinate system. So by using this, we will get the value of angle, because we know we can calculate it. And so, another remark, in coordinate system, I will use directly. The cosine theta will be written in a product of u and v over no u, no v. It is same to cosine theta is no in a product of vector u and v. So by this definition, we can get the value of theta. And also, that means the cosine theta gives the cosine theta's image is in -1 to 1, as the cosine theta is in -1 to 1, so it also means the norm of u, norm of v, u, the product of v norm is in its absolute value is less than or equal to 1, and from this we might consider the Cauchy-Schubert the inequality by called it Cauchy-Schubert inequality. Of course, it is not formal proof. However, I will explain in this class like that. If you want to prove the Cauchy-Schubert inequality, it is called Cauchy-Schubert inequality. By performing projection, and you might get the value of them, because if you give two vectors, then the projection will give more. I think it is not good. Not good explain how by this length will be shorter than this length because it is cosine. It will calculate cosine theta, and so the length is less than this, and so the norm will give more shorter length, a shorter value, smaller value than the product of the norm. So the value will, if you use projection, then you can prove the inequality. Let me check the property of inner product. So let u, v, and w be a vector, b vectors in R to the n, and let k be a scalar. the by the definition of norm, oh, I by the definition of norm, it has commutativity because it is same v1 u1 plus v2 u2 vn un. So the first property is commutativity, or sometimes it is called the symmetric property. Symmetry property. And the inner product also has distributive rule, because it is also same. We just calculate for each vectors, and the addition is also calculated each vector, so it is same to the distributive row in real number. And the next, it is called the homogeneity. However, I think it is similar to compatibility or the associative rule. By calculating the inner product first, it is same to calculating scalar multiplication first. And it is also trivial by using the notation, the definition of inner product in there, because it is calculated for each vectors. So it is makes sense. Homogeneity. And the last one is we have seen that the inner product itself is bigger than 0, and if it was 0, then the vector v was mean 0 vector. We constructed the multiplication between vectors. However, it is very similar to the dot products, very similar to scalar multiplication, because it will be calculated for each vectors, and so it gives similar properties with a similar property to the scalar multiplication property. It is that theorem. I will use same notation. So if you inner product 0 vector and v vector, then it will give 0, because for each vector is 0, so it is same to scalar multiplication. And as like the scalar multiplication has distributive rule, it has also in the product also has distributive rule. And right distributive rule also makes sense, and although we use subtraction, it is defined by addition, and so it is also satisfied the left distributive law of the vector. And C and D. I will use A, B, C, D, E. Left multiplication and right, left action and right action. Action is multiplication. 네. 잠시만요. And finally, the scalar multiplication gives for each vector also, because it will calculate for each vector, so the scalar multiplication will effect to be for each vectors, so it is also makes sense. And we have in triangle system, we know the special property. It is called the triangle inequality. I use this form. If you calculate the length of each edges, if you calculate length of the each edges, then if you sum two lengths, then it will longer than another way, because its length is just this straight line. However, it is the longer line, and it is makes sense by choosing another two vectors like v plus v minus w is bigger than w, and this form is called the triangle inequality. Triangle inequality. And so in vector space having inner products, they give same property. I will use same notation. U, V, W, E are vectors in R to the N. Then the norm of addition of U plus U and V is smaller than, is less than for each norm's summation, each norm's addition. It is called the triangle inequality. And also, I say its length as the length, so this triangle inequality is satisfied in the notion of distance. That means if you give some position for a vector u, then it will give these three distance, and the distance also has triangle inequality, and it is same the first one. If calculate the first one, if I prove of A, then by by give square roots for each side, and it has all it has positive. If it was not 0, then it will give positive value. So by calculating square root, it is also will give positive value, and it is for each vector square root of each norms. Thus I choose the square root, and then it will give I should show it. I mistake, sorry. By using the property of the definition of norm, then it will be the norm of u plus v, and we have this property of norms, and so we can use it. We can calculate it by using the above property. And also, it is the definition of the norm, and it is also by the definition of norm, it is u square plus 2u product v square, and also we by using the Cauchy-Schwarz inequality, the norm of uv will give this inequality, and so we can get the value of not the number of u addition the number of v square, and so that means the number of u plus v is u v. And actually, by using Cauchy-Schwarz inequality, we can prove this, and conversely, by using this triangle inequality, we can prove Cauchy-Schwarz inequality. So they are same property in Euclidean space. I will introduce one more property. If you learn the bilinear map or in a product in detail, then you might get this equation. It is called the parallelogram equation. And I will use UMV is in R to the n. Then u plus v square, u minus v square is 2 of u square plus v square. And by using the calculate of norm, then you can get the result, because it is u plus v norm u plus v, and it is u square, I use u square, plus v square plus 2 u inner product v, and this is same to u norm plus v norm minus 2u inner product v. So just calculating this, you can get the property that is quite useful too, because by calculating we will change the coordinate them to the single coordinate. And also conversely, it is calculated by norm. However, we can calculate in inner product, and it is also easy to calculate it to get the equality by calculating the norm, because it will give 2uv and minus 2uv, and the coefficient is 4, so 1 over 4, so it will give the u square v square plus 2u dot product v minus 1 over 4 u square v square minus 2u dot product v, and calculating this, you can get the result u in the product v. So these two equal equation is quite important in a product space. It is called in a product space, and firstly I say the space has structure, and if the structure was in a product, then it is called in a product space. And in this space, these two equalities very important, and every inner product space, if you bring any arbitrary inner product space, it is divided. Also, finally, it is in if you study more in linear algebra, then I explained the rotation or reflection, the transformation, and this transformation, if you consider them, then by using the normality, the transformation will move the vectors to another vectors. However, if it preserves the length, then it will be called the orthogonal transformation. And in the next chapter, we will study about orthogonality, and so I will give this remark. Let u and v be vectors in R to the n. Then the inner product AU inner product V, it was the product for each vectors, so we might be able to denote U inner product V as the matrix multiplication V transpose U, because it will be written V1, V2, Vn, U1, U2, Un, and it will multiply for each vectors, and so it is same the definition of inner product. So in this sense, we might be able to write this as matrix multiplication V transpose matrix multiplication AU, and by using associative rule, we can calculate that V8 transpose matrix multiplication U, and it is same U in a product V8 transpose. So if you can move the matrix multiplication to you can calculate the linear transformation to vector U, and by performing the transpose, and you can get the transformation of the transformation to V. And similarly, if you calculate U in a product AV, it is AV transpose matrix multiplication U, and it is V transposition A transposition in a product U. It is matrix multiplication U. And by using associative rule, you can get V transpose matrix multiplication A transpose matrix multiplication U, and it is same A transpose U in a product V. And so the matrix can move the first vector to the second vector by performing transpose. Oh, maybe I mistaken here. I thought it is weird. A transpose V, and so A transpose in here it is A transpose V. So the position did not change, just it will be performing transpose by moving another. And furthermore, we performing two property both, then it will move A transpose and it will move A transpose, so it gives the A transpose U in a product V. It is true because A is, if you operate transpose double, then it will be original matrix. It will be same to original matrix. Okay.